Afternoon, everyone. Come on in. Today's music brought to you by I have no rhythm. Absolutely no rhythm. My piano is bad at best. Good afternoon, everyone. Come on in. Good afternoon, everyone. Tribute to Raymond Lévesque, who passed away last night. A monument of a man, poet, playwright, singer-songwriter. This song is so big amongst the Francophone community. Many of the French artists have re-recorded it. Most play it often in their shows or whatever. Huge. I don't really play any instruments. I mean, everything is, it's bad. I do play a little piano, but I mean, I haven't touched a piano in probably a decade. All right, how are we doing? When will we finish material for the midterm? Probably this week. Now, air guitar. Something I can get behind. Maybe I should adopt that as my answer next time somebody asks me if I play an instrument. All right, questions? Well, here's a question that arises naturally. We did the simplex method for the standard maximum problem. For the standard minimum problem. But what if you have a non-standard problem? What if you're maximizing a function where the inequalities are going the wrong way? Or if you're minimizing a function and the inequalities are going the wrong way? What then? Because the standard maximum problem is very pointy. And similarly with the standard minimum problem. So what if you have a non-standard problem? The simplex method can be adapted to that. And let's see how to adapt. It's really a question of the inequalities going the wrong way. So let's illustrate with an example. Well, let me tell you what we can do, and then we'll illustrate with an example whose solution we can already work out in a different fashion. Imagine the inequalities going the wrong way. 2x plus 3y bigger than or equal to 5. Right? When the inequalities were going the other way, we would add what is known as a slack variable, which would pick up the slack left behind to transform the inequality into an equation. Here, we will oftentimes have too much. Right? We're going to have too much things, right? If x is 4 and y is 3, 8 plus 9 is 17, that's way bigger than 5. We have a surplus here. So we're going to introduce what is known as a surplus variable. We're going to introduce a positive variable where 2x plus 3y minus s1 is equal to 5. Right? So a surplus variable which transforms the inequality into an equation. So very much like a slack variable, except that we're going to subtract it here to transform the inequality into an equation. And that's the idea. So let's illustrate with an example. Consider this. Here we have a non-standard problem, right? Because in a standard problem, all the inequalities are less than or equal to something positive. And here we don't have that. The inequality is going the wrong way. Right? If you're thinking to yourself, well, I'll just bring the 20 there and that to the other side, but then you get less than or equal to negative 20, which is less than 0. So that doesn't work either. What we're going to do is we're going to introduce slack and surplus variables to pick up the slack from here and pick up the surplus from there. Thank you. There should be an X2. Thank you, Lance. So let S1 and S2 be bigger than or equal to 0, transforming these inequalities so here I'm introducing a surplus variable minus S1, and here a slack variable there it is. And as usual, let's rewrite this way. And now these three together, we can consider our simplex tableau. Where we'll reserve the first column for x1, second column for x2, s1, s2, z, and the constants. What do we have? 2, 1, minus 1, 0, 0, 20, 2, 5, 0, 1, 0, 80, and minus 6, minus 2, 0, 0, 1, 0. Right, so the usual. However, we don't right away start as we normally would. This is a non-standard problem. And if you take a step back, if you were to treat this as essentially a final simplex tableau, is the video quality poor? Seems not too bad from my end. How's everybody else? Good? You know, I'm broadcasting through Videotron, and frankly, over the weekend, Videotron had its issues. All right. What I want to point out is, if you treat this as a final simplex tableau, right, in the sense that we can read off the solution here. Here, x1 doesn't have any leading 1, so x1 is 0, x2 is 0, s1, even though we didn't turn this into a positive 1, right, I mean, you could multiply the whole equation by negative 1, and you'd see that s1 is negative 20. S1 is negative 20, and that's an issue because we are assuming S1 and S2 being bigger than 0. So we want to address that immediately. And that's what's going to dictate our pivot as far as we're concerned. So we want to address the negative variables first. So we're going to look at the leftmost entry in that row, right? So the -1 occurs in the first row. So we're going to look at, we're going to go until we have non-zero entries here, the last non-zero entry in that row. And the pivot is going to live in this column. So the usual thing now, smallest quotient, 20 over 10 versus 80 over 2. And this is the pivot. Now, I know what you're thinking to yourself. This coincides with exactly the same pivot as we would normally have had, and that is coincidental. Coincidental in this example, but that's what happens. So we'll use this 2 to clear out the column. Row 2 minus row 1 for row 2. Row 3 plus 3, row 1 for row 3. And 1/2 row 1 for row 1. So this minus that, this minus that. And this plus 3 times that, this plus 3, this plus 3. This plus 3. All right. Sure. If 2 rows have negative numbers, I mean, you could, again, right? I mean, this idea is very artificial, but as long as you pick a rule and stick to it, maybe start with the one that's on the right, the most right, or the most left. It really doesn't matter, but as long as you keep that rule going throughout the whole question, that would be fine. So if you want to say the one that's on the leftmost, and always keep leftmost, makes a lot of sense to do that because we already are using leftmost for another rule. So let's define it this way. So leftmost it is. All right. Now, let me bring your attention to the fact that perhaps you're thinking to yourself, I still have a negative here, but viewed as a final simplex tableau, this does not have a leading 1. So S1 would be 0, thereby having removed the issue. But this is not the final simplex tableau, right? Because now we move on to the negative numbers in the last row, and we still have negative numbers. So here we have a negative number. So the pivot is going to live in this column. You know the pivot cannot be negative, so this will have to be the pivot. So let's use this one to clear out the column. Row 1 plus 1/2 row 2 for row 1. And row 3 plus 3 row 2 for row 3. I probably should have left that there and maybe wedged the answer in here. It's too late for that. Too late. What do we get? And 24 to 40. And there it is. So you see, x1 is 40. x2 does not have a leading one, right? I mean, first of all, I probably should mention this is our final simplex tableau because there are no more negatives in here. x2 is 0. S1, 60. S2 does not have leading one. S2 is 0. And Z is 240. A few questions here. We'll do another example. Yes. If two rows have negative variables, we just follow the normal pivot rules to pick which one we use. Let's go with leftmost. I mean that's our. Once you make row operations, if you have any negative things in the last row, you want to choose another pivot. I mean, right, first let me point out, the first important step is to get rid of negative variables. That's the first thing, right? So here, S1 would have to be negative 20. And we know that that's not possible because we want our variables to all be positive. So we have to address that first by bringing our attention to the leftmost non-zero entry, and our pivot will live in that column. So that's the only difference between standard and non-standard problems. The possibility of having negative variables to begin with. That's what we want to address first. So that's how we got, right? I mean, again, let me point out, this is telling me that S1 has to be negative 20, which is impossible. So we want to address that. Leftmost column, which has non-zero entries corresponding in the first row, right? So the pivot will live here. So smallest quotient again, and do your pivot operations. After doing the pivot operation, even though we still have a negative here, this doesn't have any leading ones. So S1 is 0. We have removed the negative variable. Until now, we still haven't used the slack variable as an answer. I mean, it never is an answer, right? I mean, we are looking for x1 and x2, right? We were trying to maximize, I forget the question now, but let's see if this made sense. 6x1 plus 2x2 subject to this does this work? If x1 is 40 and x2 is 0, we get 240, looking good. And 80 plus 0 is bigger than 20. And 80 plus 0 is less than or equal to 80. Everything looks good, right? Here, the surplus, right? I mean, this is 80 compared to 20. The surplus is 60. Here, there was no slack. 80 is equal to 80. No slack. The pivot can never be in the bottom row, correct? So this is how you can address non-standard maximizing problems. What about minimizing? Well, if you're minimizing a function, let me point out that minimizing a function is the same as maximizing negative W. Right? If you're minimizing a function, it's like maximizing its negative. What's the biggest? Yeah. So let's illustrate. Minimize. Exactly that. After we've gotten rid of the negative variables, right? Because there could have been more, right? There could have been more. There could have been some negatives here as well. Yeah, I mean, right? I mean, you could have had theoretically a leading -1 somewhere there. You would have wanted to address that and then move on to the last row in a traditional way. Exactly that. Consider this. Let me point out that this is a standard minimum problem. So you can evaluate this in the standard way. Right? By setting up a matrix, taking the transpose, and finding the dual problem. And I'll leave you to do that. It's a nice exercise. You can also solve this using the graphical method. But we're going to solve it as a non-standard problem. Because, you know, I mean, a standard problem is still a non-standard problem. There's no issue there. This non-standard business is just a generalization. Right? So here we have these inequalities. So first of all, instead of minimizing that, we're going to maximize its negative, which is -3y1 minus 2y2. So now we have a maximizing problem, but the inequalities are going the wrong way. So we're going to introduce surplus variables where y1 plus 3y2 minus s1 is equal to 6, and right, and as usual, let's bring this to the other side. So we get 3y1 plus 2y2 plus z is equal to 0. Let's set up our simplex tableau here. 1, 3. Minus 1, 0, 0, 6, and in this business, 3, 2. Why don't we switch the signs of the conditions when we make the function negative? Well, I'm not changing the domain, right? I'm suggesting that minimizing this function is equivalent to maximizing its negative. Right? If you have two numbers, 2 and 7, of course, this is the smaller of the two. If you look at their negatives, -7 and -2, this is the bigger. So, right, I mean, you see, if you multiply the whole thing by -1, it's not these inequalities that I'm trying to convince you of, it's that minimizing a function is the same as maximizing its negative. All right, so now you see that you have two negative numbers, right? S1 should be -6 and S2 should be -3. We had agreed on, what have we agreed on, right? So first of all, you've got two negative numbers here that you want to get rid of. We agreed on a rule that says most, the leftmost. So leftmost is this one. Let's try to get rid of that one by looking at the last column with non-zero entries. So the leftmost column with non-zero entries. That's the last column here, smallest quotient, 6/1 versus 3/2. 2 is our pivot. Thank you, Annie. Let's change it into a 1, 1/2 row 2 for row 2. And this is still our pivot. Let's use it to clear out the column. Row 1 minus row 2 for row 1. Row 3 minus 3 row 2 for row 3. What is that? that is nothing. There's no, copy that down. This minus that. This minus that. So 5 over 2. This minus that. This minus that. 12 minus 3 is 9 over 2. This minus 3 times that. And this minus 3 times that. Minus 9 over 2. Oliver is asking how is 2 the pivot. First of all, we have 2 issues, right? 2 of the variables are negative. So we have to get rid of them. We said we were going to focus on, we're inventing a rule here. Leftmost. So this one, we're concentrating on that one. Look at the most leftmost entry in that row, which is non-zero. It's this one right here. So pivot is going to live here. Smallest quotient, 6 over 1, 3 over 2. 2 is the pivot. Right, and Britton is pointing out that we still have a negative variable here. Right? S1 is still negative 9 over 2. So we repeat. Or are we using this method instead of the transpose? Well, you know how to do the transpose. I'm just saying that the method of non-standard, so the non-standard method can be adapted here as well. Right, and as Britton suggests, we still have that issue. S1 is still a negative variable, so we want to address that. Go to the leftmost column without 0 entry, right? So now the second column is the important one. The pivot is going to live in the second column. 9 over 2 divided by 5 over 2, that is 9 over 5 versus 3. And 9 over 5 is the smaller of the 2. Thank you, Annie. 5 over 2 is your new pivot. All right. What do we want to do? Do we want... Not very nice. All right, let's change it into 1. 2 over 5, row 1 for row 1. How can we judge if it's standard or non-standard? Well, you have the definition of standard problems, right? Either standard maximum or standard minimum. We gave those definitions last week. If it's non-standard, that usually means the inequalities are either going the wrong way or you have the two types of inequalities. And then this method always applies. If you have a standard maximum problem and you're working with the non-standard simplex method, it's actually exactly the same thing. There won't be a difference between standard maximum approach versus the non-standard approach. That was our pivot. The 1 is the pivot. Let's use the 1 to clear out the column. Row 2 minus 1/2 row 1. Row 3 minus 1/2 row 1. So this minus 1/2. This minus 1/2, this minus 1/2, this minus 1/2. So 5 minus 1 is 6/10. I want to say, what am I doing? This minus 1/2. So 6. Minus 6/10 or minus 3/5. This minus 1/2. So 15 minus 9 is 6/10. 3/5 again. Three over 2 minus 1/10. 15 minus 1 is 14/10. 7/5. Is somebody working these out just to make sure? Minus 45, so minus 54/10. Minus 54/10. Minus 27/5. Anybody? Well, we'll check if that makes sense. First of all, observe now that no variables are negative. That was our first concern. That's taken care of. And then no negatives in the last row either. So this is the final simplex tableau. Y1 is 3/5. Y2 is 9/5. S1 is 0. S2 is 0. And Z, which was negative W, is negative 27/5. So W is 27/5. That's the minimum. Let's recall what the inequalities were, just to see if that makes sense. What did we have? We were trying to minimize this is subject to this. Let's just see if that's anywhere near what we should have. 9 plus 18 is 27 over 5. Looking good, looking good. 27 plus 3 is 30. 30 over 5 is 6, so no surplus. And 6 plus 9 is 15 over 5, which is 3. No surplus there as well. Exactly, looking very good. Can we re-explain why this is the final simplex tableau? In the non-standard approach, two things you want to be careful of. The first thing, you don't want any negative variables. Here, y2 is 9 over 5, y1 is 3 over 5, s1 is 0, s2 is 0, so we're good to go. Then, following the regular simplex approach, you don't want any negatives in the last row, and you don't. So we're done. Why wasn't the third to last matrix the final simplex tableau? Why wasn't this the final simplex tableau? And the reason is, this is the column for S1, and you see that S1 would have been negative 9 over 2. And we don't want negative variables. So that's why we still had some work to do. Of course, at any step of the way, if it's impossible to find a pivot or impossible to continue, that just means there's no solution. Questions? Well, the third to last one, I mean, we're still working with non-standard, right? Because here you have a negative variable. Yeah. I mean, the original, by introducing surplus variables, we're treating this as a non-standard problem. How are we doing here? Right, the last matrix has a negative here, but of course, if you go back to what we were doing, we were looking at z equals negative 3y1 minus 2y2, and y1 and y2 were both positive, so we have absolutely no control over that. Of course, we're going to get a negative answer. So, yeah. So we disregard, and anyways, I mean, yeah. So disregard that. Can we only use surplus variables to solve minimizing problems rather than the transpose? I mean, now you have options, and you can use whatever you want. Okay. And as this suggests, I mean, I'll invite you to redo it using the transpose and also using the graphical method. All three approaches work. And he's asking which is more effective. It's a valid question. It's a valid question. I don't know which is fastest. Because, these are very simple. You've only got 2 rows. Yeah, this method does seem faster. It does seem faster. I don't know that I want to jump to that conclusion, though. All right, questions? This is it for the simplex method. Standard and non-standard problems. It's all good. Questions? If there are no questions, we'll move on to a new topic. Interest rates. Normally you do some of that in 122. I know some of you might not have done that course. I don't know if you did interest rates in 122. So we'll do it from scratch. It's all good. We'll lay the groundwork today, and on Thursday we'll introduce new ideas. I'm sure you're all somewhat familiar with interest rates anyways. Let's take an example. If you place $100 in the bank at 8% annual rate, after a year, you will have how much money will you have? Well, you will certainly have your $100. And then you'll have the interest on $100, which is $8. Question: what if you leave that money in the bank for another year? Well, now we have to make a distinction between simple interest and compound interest. In simple interest, you do not earn interest on the interest. So in simple interest, you only earn interest on the capital. Essentially, it's like the bank paying you that $8 and you keeping it in your pocket. So you still have just $100 in the bank, and you're going to accumulate interest only on that $100. But if you left the whole $108 in the bank and accrued interest on that, so for another year, after year 2, you would have the original 100 and 2 times the $8. So 116. Exactly that. In simple interest, you only earn interest on the original amount, on the $100. And after 3 years, it's 100 plus 3 times the $8, so 124, and so on. So in the simple interest case, it's very easy to come up with a formula in general. If P is the principal, I is the simple interest, and N is the years, the accumulated amount you've got your principal and the interest on the principal times the number of years. Right? The interest on the principal, so that's your 8, times the number of years, 2, 3, 4, or N years. Or if you want to factor out a P, 1 plus IN. So that's the accumulated amount if you're using simple interest. Compound interest, however, pays interest on interest. This is how banks really work. You get interest on the interest. So, after 1 year, it's still the same thing. It's the $100 plus the interest on the $100. But if you leave the money in the bank for a second year, that's where the compound interest So after 1 year, you still have the 100 plus 100 times 0.08 times the $8. But after a second year, it's like leaving the $108 in the bank for a year. So after that year, you'll have the $108 plus the interest on that $108. And if you factor out 108, you get 1 plus 0.8, which is really what this was anyways, right? I mean, this was, if you factored out 100, it's really 100 times 1.08. So this is really 100 times 1.08 all squared. And if you leave it for a third year, you see what's happening, right? If you leave it for a third year, you'll have that amount plus the interest on that amount. And if you factor this, which is common to both, what are you left with? 1 plus 0.08, or another 1.08 again. And so on and so on. In general, if P is the principal, I is the annual rate compounded annually. And N is the years. The accumulated amount is your principal, 1 plus the interest, to the power n, right? 1 plus I cubed, 1 plus I squared, 1 plus I. There it is. Let's illustrate with a few examples. The question, let's do 12 first. The question is, find the maturity value and the amount of simple interest earned if you place $12,000 in the bank at 5.3% for 11 months. Right, so 5.3%, this is an annual rate, but only for 11 months. So our accumulated amount is the principal times 1 plus I times the number of years, but here you're not even leaving it for a year. Instead, you're leaving it for 11 months. So principal, 12,000. The interest rate, 5.3% or 0.053. And 11 months in years, what is that? Well, that's 11 over 12. Not even a full year, but 11 over 12. Can somebody work that out on the calculator and tell us what that is? I'll let you work that out. $11 over 12, correct? 12,583. Were there some cents there? We want to round off to the nearest cent? No? Oh, that was it? It was whole, thank you. Very well. 14. If 23,500 earned simple interest of 1,057.50, in 9 months, what was the simple interest rate? All right. There it is. So how much interest does this earn? 23,500. This is going to earn some interest for 9 months. So 9 out of 12. And apparently it's this much interest. So solve for I. I is easily seen to be 12 over 9 times 1,057.50 divided by 23,500. Somebody work that out for us? %6? Is this rounded or is the exact number? Exact, thank you. Everybody with us here? How are we doing? Consider the following scenario. Find the compound amount for each deposit and the amount of interest earned if you are depositing $1,000 at 4.5% compounded annually. For 6 years. Now, this brings up an interesting issue. What about the 1 in P times 1 plus I to the 1 plus I, right? I mean, I didn't need to use that here. I mean, you could have used that, right? I mean, we're saying that the principal, which was 23,500, if you accumulate that for 9 months, so 9 out of 12, this should give us what? This accumulated amount So it should be the original plus the interest. So that should have given us 24,557.50. Right, so if you want to use that formula, that's what you should have written down and then solve for I. But I claim it's going to be the same thing as this. I'll invite you to do it, right? But I mean, if you expand this and you bring the 23,000 to the other side, you subtract it, and you'll be left with that. And then it's exactly this on the left. And let me point out, that the book is going to throw out to you a bunch of formulas. And I'm not a fan of that. I'm not a fan of that because you can always work with either this one or the associated, the equivalent compound interest one. And don't try to learn a bunch of formulas by heart. That's just terrible and really counterproductive. Instead, one good formula is all you need. Here, what are we doing? We're placing $1,000 at 4.5% compounded annually for 6 years. How much money are we going to have at the end of the 6 years? So our accumulated amount is the principal one plus the interest for the number of years, right? So here, principal is 1,000. Interest is 4.5% or 1.045. Number of years is 6. What do we have here? Exactly, Annie, right? 1,057.50 is the interest earned, not the principal and the interest. So that's why I just had this, because this is really the interest you earn on the 23,000. Thank you, Lance. 1,302.26. Thank you, everyone. The question was twofold here. What is the accumulated amount? So this is the accumulated amount. This is the amount you'll have in your bank account after 6 years. The interest earned is, of course, easily seen to be, you started out with 1,000. So the interest earned is the rest, right? There it is. Now let me ask you this. Easy enough. I'm sure you've all seen this before in some form or another. But now, what if the interest is paid more often than once per year? What does 5% compounded monthly mean? What does a 5% rate compounded monthly mean? Does it mean 5% every month? Or does it mean 5 divided by 12% every month? Both answers kind of make sense. So let's define it definitively so that there's no confusion. definition, an annual rate of I compounding m times per year, right? So here compounded 12 times per year. Exactly, right? If you want to make a contribution to your portfolio every week or every month, every year. So an annual rate of I compounded n times per year means a rate of I over m every period. Right, so 5% compounded monthly, an annual rate of 5% compounded monthly means 5 over 12% every month. The formula we had before, the accumulated amount, so in this case, everything extends immediately, but instead of I, you have I over m, and here n is the amount of periods, not years. Right, so it's like every month is a year corresponding to the adjusted interest rate. Let's illustrate. Same question as before. Now we have 15,000 at 6% compounded monthly. For 10 years. Right, so again, do not confuse this to mean 6% every month. It doesn't mean 6% every month. It means 0.5% every month. So the accumulated amount is going to be your principal, 1 plus I over m times the number of, well, to the power number of periods. Here, you're starting out with 15,000. 6% divided by 12, or let's say 6%, so 0.06 divided by 12, to the number of periods. There are 12 months in a year for 10 years, so 120 months total. So this is really 15,000, 1.005 to the 120. Somebody work that out for us. Anybody working that out? 27,290 and 95. Thank you. You know, it's important for you to work these out on your calculator. Don't wait until the midterm to realize that you don't know how your calculator works. I've seen it happen. Get acquainted with your calculator because this is going to be needed here. Well, first Julia is asking, how do we find 120? This is the number of periods, right? This interest rate is per month. There are 12 months in a year, so 120 months in 10 years. Brendan is asking if it's, I am assuming it would be acceptable for us to use other versions of this formula. That's the thing, right? I mean, the book has a bunch of formulas and you get lost in the formulas. I claim this is the important formula. This is the only important formula. Everything can be brought back to this formula. Okay, fine. Yes. Here they're using NT instead of N, where M is the number of periods per year, and T is the number of years. It's the same thing. It's really the same thing. All right, let's do one more. Let's do one more. Same question, 9,100 at 6.4% annual rate, compounded quarterly. For 9 years. What does compounded quarterly mean? Compounded quarterly means every quarter, there are 4 quarters in a dollar. So 4 quarters in a year. Every quarter is 3 months. So same formula as always, the accumulated value to principal. So principal, 9,100. 6.4% quarterly, so there are 4 quarters in a year, and you're doing it for 9 years. So 4 quarters a year for 9 years. How many quarters in total? 9 times 4, 36. Somebody work that out for us. Thank you, Lance. 16,000, 114 and 43, rounded to the nearest cent. Absolutely. Thank you very much. There it is. So practice this idea of interest. I mean, again, you might have seen it in 122. You might have seen it in high school. It's very elementary stuff, but very important because we're going to start asking important questions on Thursday. How are mortgages calculated? how are pensions calculated? You borrow money to buy a car. How do they calculate the monthly amount you have to pay? These are all excellent, crucial questions, and we'll consider those on Thursday. Thank you all for coming, and I will see you then. You guys have a good one.